A modern video model can generate a realistic car crash. Glass shatters, tires, smoke, the camera shakes, and the whole thing looks physically convincing. But a world simulator has to answer a harder question. Would that crash still happen if the driver turned 2 degrees earlier? What if the road was wet? What if a pedestrian stepped in from the left half a second later? That is the difference between plausible video and controllable consequence. Video generation asks, what sequence of frames looks likely? World simulation asks, what state is this world in? What actions are possible? And what happens if something intervenes? That distinction is becoming one of the biggest ideas in AI. The next frontier is not just models that generate clips of worlds. It is models that can simulate worlds you can act inside. The phrase world model did not start with Sora or video diffusion. It comes from control, reinforcement learning, robotics, and cognitive science. A world model is a learned model of how an environment changes. The simple version is observation plus action plus hidden state gives you a predicted future state. If a robot sees a cup on a table and it moves its arm forward, what happens next? Does the cup move? Does it fall? Does the hand miss? A world model is the system's internal guess about that future. This matters because an agent can use the model to imagine before acting. Instead of trying every action in the real world, it can run short internal rollouts. That is the core idea behind systems like world models, Dreamer, and model predictive control. The model does not need to render a beautiful video. It needs to be useful for choosing actions. That is the first important split. A world model is not automatically a video generator. It is a dynamics model. The visual frame is only one possible surface of a deeper prediction problem. So why are people suddenly calling video generators world simulators? Because video is dense with physics, every real video contains motion, lighting, occlusion, camera movement, object permanence, human behavior, and cause and effect. A ball falls. A car follows a road. A hand grasps a tool. A person walks behind a wall and comes out the other side. Train a huge model on enough video, and it starts to learn some of those regularities. It may not learn Newtonian mechanics explicitly, but it learns patterns that look like physical dynamics. That is the argument behind OpenAI's Sora framing. Scaling video generation may be a path toward general-purpose simulators of the physical world. But this is where we have to be careful. There is a huge gap between simulating the world and simulating the distribution of videos humans record of the world. A model can generate a beautiful clip of a person walking through a room while still losing track of where the door was, what object they picked up, or whether the geometry remains consistent after the camera turns. Photorealism is not the same thing as physical understanding. The real shift happens when the model becomes interactive. A passive video model takes a prompt and produces a clip. An interactive world model takes a prompt, an observation, and an action, then changes the future based on that action. This is why systems like DeepMind's Genie are important. Genie learned to create controllable, game-like environments from video. It did not require every video to come with perfect controller labels. It inferred a latent action space from the visual data. That sounds subtle, but it is a major step. It means the model is not just predicting what comes next in a video, it is learning something about the actions that could have caused the video to change. This is the bridge from watching worlds to acting inside them. Imagine a generated environment where an agent can move left, jump, open a door, or push an object, and the world responds consistently. That starts to look less like a movie and more like a learned game engine. But the word learned is doing a lot of work. A traditional game engine has hand-coded physics, explicit objects, collision rules, and a structured scene graph. A neural world simulator has learned fuzzy dynamics from data. It can be more flexible, but also less reliable. The hardest problem is memory. A convincing world simulator needs more than frame-to-frame smoothness. It needs persistent state. The red cube behind the wall should still exist. The door you opened should stay open. The glass you broke should stay broken. The room should not quietly rearrange itself when the camera pans away. This is where many generative systems fail. They produce locally plausible frames, but the world underneath is unstable. Objects mutate, characters drift, layouts change. The world becomes rubber, smooth on the surface, but structurally soft. A real simulator needs an invisible state beneath the pixels. It needs object identity, spatial layout, scene history, agent actions, and some representation of what has already happened. You can think of the rendered frame as the tip of an iceberg. The hard part is under the water: geometry, physics, memory, uncertainty, object permanence, and causal state. This is also why the phrase persistent dynamic memory matters. Whether a system uses memory tokens, latent recurrent states, scene representations, or external maps, the goal is the same: preserve the world over time. Without memory, you do not have a world, you have a sequence of convincing hallucinations. This matters far beyond video generation. Robots and autonomous vehicles need practice. Real-world data is expensive, slow, risky, and incomplete. You cannot crash millions of real cars to learn rare edge cases. You cannot have a household robot break thousands of dishes to learn manipulation. A good world simulator could create cheap practice environments. It could generate rare driving scenarios, alternate futures, unusual object interactions, or synthetic robot training data. That is why systems like Gaia, one for autonomous driving, and NVIDIA's Cosmos-style world foundation models are interesting. They point toward world simulation as infrastructure for physical AI. The loop is simple. Observe the world, update the world model, imagine possible futures, choose an action, act, and observe again. But safety-critical domains raise the bar. For entertainment, plausible motion may be enough. For driving, it is not. A simulator has to be correct under intervention. If you change the steering angle, road friction, speed, or reaction time, the future should change in a physically meaningful way. A generated crash that looks real is not enough. The counterfactual has to be right. So, are world simulators the path to AGI, robotics, and embodied intelligence? Maybe. But the honest answer is, we are early. Current systems are impressive learned visual dynamics engines. They can generate scenes, motion, and sometimes interactive environments. But they still struggle with long-horizon consistency, exact physical causality, controllability, and rare events. Benchmarks are also immature. How do you measure whether a model understands physics? Do you check if the video looks good? Do you test object permanence? Do you run counterfactual interventions? Do you train an agent inside it and see if the behavior transfers to reality? All of those matter, and none of them are fully solved. There is also the sim-to-real gap. If a robot trains inside a flawed, generated world, it may become very good at exploiting that world's mistakes. It may learn shortcuts that do not work outside the simulation. So the balanced view is this. World simulators are not magic physics engines. They are not yet reliable replacements for traditional simulation. But they may become a new layer in the stack learned, flexible environments that help agents practice, plan, and understand possible futures. The important shift is not just that AI can make better videos. The important shift is that video, action, memory, and prediction are starting to merge. A language model predicts the next token. A video model predicts the next frame. A world simulator tries to predict the next state of an environment, especially after an action. That is a much bigger target. If this works, future agents will not only talk about the world, they will practice inside learned models of the world. They will imagine futures, test plans, and improve before touching reality. But the trust problem remains. A world simulator is only useful if its hidden state is stable enough, its physics is consistent enough, and its counterfactuals are accurate enough to matter. That is the frontier. Not just generating worlds that look real, but building worlds that behave coherently when you act. Subscribe to AI Deep Dive for more technical breakdowns of where AI systems are actually going beyond the demo videos and into the machinery underneath.